so in this one we're given the infinite sum of -1 to the n times n to the fourth over n to the third plus 1. So we're asked to determine, and I'll write it up here, whether this sum or series converges absolutely, so I'll just write this, absolutely, conditionally, or does not converge at all. So one of these three things it does. Okay, so let's look at, let's test for absolute convergence first. So for absolute convergence, then that means that the limit, essentially the limit as of the absolute value of the sequence. So this is our an, right? This is an. This must converge, basically. It has to equal a number. So we're asked, what does this equal? So this is n goes to infinity of -1. Well, okay, here's another useful, well, I'll write it out for now, but we'll just write this. So then n to the third plus 1. Okay, so by writing it this way with the absolute value signs, you can see that absolute value just means everything that's within here is going to come out as a positive number, right? So this -1 in front here, that's going to become insignificant, because even if it is a -1, it'll just come out positive anyways. So we can kind of ignore that, so that's good. And at this point, I'm going to use the useful, represent this as f of n, or, I mean, we've seen this before as f of x, right? So I'll use this one. It means the same thing, basically, but you'll see why. So I'll rewrite this as limit as x goes to infinity. I'm going to replace the n's with x's. So now we have x to the fourth over x to the third plus 1. And I just rewrote it like this, so, well, okay, again, like I said, you'll see. So let's try plugging in infinity. So we have infinity to the fourth over infinity to the third. Okay, that's an indefinite form, so we have to utilize L'Hopital's rule. L'Hopital's, that good old guy. Okay, so, I mean, when I use L'Hopital's, I make sure that it's an x form, just because. I don't know if that's mathematically correct or not. I feel like it is, so let's just utilize it in x form. So we have limit as x goes to infinity. So we're going to take the derivative of the top over derivative of the bottom. So that would be 3x squared, right? And then we can keep rewriting the absolute value signs here. But I mean, technically we don't have to have the absolute value signs, because as you see, our interval goes from 1 to infinity. So anything that's, well, these x's are going to be positive anyway, so it doesn't matter. But as you can see here, if we try plugging in infinity, we're going to get the same indefinite form. So we have to keep going. So then this is going to equal limit as x goes to infinity. And I'm just going to get rid of the absolute value sign. So 12x squared over 6x. And then this again is going to infinity over infinity. Same old story. And then I'll continue on the next slide. So keep this in mind, this last thing. And then we get that the limit as n goes to infinity of 24x over 6. And this we can just, I mean, that's 4 over 1. So limit as that. So then we could plug in infinity, and that is not an indefinite form because we don't have it over another infinity term. So what we have here is that this diverges, right? So that means that it cannot converge absolutely. That means, because infinity implies divergence. So divergent, diverge, hold on. Wow, that was all tied together. Diverges. Okay, so absolutely convergent, it is not. So we ruled that out. Okay, so now let's check for conditional convergence. So I know you might be thinking, wow, that was only the first part, and yeah, I'm kind of thinking the same thing, but for these, it's a lot of like trial and error, and you have to try every single case, basically. So now we're going to check for conditional convergence, and this is where we use the Leibniz test. For Leibniz test for alternating series. Alternating series. Okay. So for here, we have, well, just to refresh, our sequence was characterized by this, n to the fourth over n to the third plus 1, okay? So for Leibniz test to work, we have to have, an has to be positive for our interval, which is from, so n goes from 1 to infinity. Well, it includes 1, so square bracket there. So anytime you plug in this basically means n is going to be positive, so yeah, it's positive. This an is positive on all values for n, so that's good. So check. And is it decreasing? Decreasing. We have to figure out if that's true or not. So let's plug in some values. Let's start with a1, that's 1 to the fourth, over 1 to the third plus 1, that's 1/2. And then we have a2, 2 to the fourth, over 2 to the third plus 1. So that would be 16 over 8 plus 1 is 9. And that is not less than 1/2, right? Because decreasing means that your a sub n plus 1 is less than the previous one, right? That means that the next term is always going to be smaller than the term that you're on right now. So this is not, so that's not less than that. Or, yeah, the arrow's going that way. So this is 16 over 9 is greater than 1 over 2. So basically, it doesn't fulfill the conditions for the Leibniz test. So that means that just inherently that this diverges. But I'll continue on the next slide to explain a little bit further. So what this is saying essentially is that we know that it's alternating because it has the factor of -1 in the front. Because it was written like this, right? And then we have our n to the fourth over n to the third plus 1. So this gives us the alternating part. Alternating, that just means alternating signs, right? So this is going to be something like, well, when n is 1, that's going to be negative. So it's actually going to be negative a1 plus a2, etc. Well, and then minus a3, dot, dot, dot. But what this means graphically is that whatever you start with, so let's say you have, I don't know, well, technically this isn't going to, well, okay, so let's say we start at 0 and then we're going to subtract a1, so that'll be over here somewhere, right, with a1 being a positive value, but the negative just indicates direction, so we're going to the left. So this is our s sub 1. And then what we said before is that a1 is going to be 1/2, and then a2 equals 16 over 9. So let's say this is -1/2, okay? So I'm going to replace this with -1/2. And then 16 over 9 is going to be somewhere, okay, let me do some math here. So this is 1/7 over 9. Okay, so this is going to be a full, like, past the 1/2 point over here. So that's 1, right? -1/2 plus 1/2 is 1. And then another 7 over 9 over here. So s sub 2 is going to be all the way over here somewhere. So that means, this is still s sub 1, that we're not converging on a certain point. We're just going out further to the sides. So this is why this series here diverges. Okay, because the terms are not decreasing. They have to be decreasing in order, well, here's our a1, let's say a2 is here, so it has to be a little bit shorter, so that eventually you kind of come up on a certain value here. But for this example, it does not, so that's why it diverges.